Okay, so we can see your presentation.
Yes. May I ask you also, I think there is some student from a university that would like to connect, but he says that he cannot enter.
Okay. Tatiana told me that now they entered. So should be
perfect. Thank you very much.
So we can check. So we can check in the process. So Francesca, please, the floor is yours.
Thank you very much. Thank you very much, Sergi, for the very kind introduction, the invitation to present, to make a lecture on force field application to nucleic acids, and for organized the third edition of this very useful and interesting school. And I enjoyed very much your previous talk. So I will, I prepare for today a pretty didactical lecture on force fields and their application to the simulation through molecular dynamics of nucleic acid. And during this talk, I will start from the approximation that are at the base of the force field, quickly explaining what is molecular mechanics and what are the force field generalities of the force field that are used commonly in the DNA simulation fields. Then I will go into some details of the common terms that are usually comprised in the mathematical equation of the force field and their relation to the properties of the system. And I will give some detail on the parameterization. So, the possibility of simulating the system, the molecules that are microscopic objects using the classic law of physics, the Newtonian law, is possible thanks to the Born-Oppenheimer approximation. This scientist now, Oppenheimer, is rightly famous also to the general public, thanks to a movie that was very successful last year, that anyway could not show all the aspects of his research. This, the Born-Oppenheimer approximation is at the basis of the force field approximation. What does the Born-Oppenheimer approximation state? That given the large difference in the mass between nuclei and electron, here in this picture are represented very roughly with particles that do not actually give the idea of what is the difference in size and in mass between electron and nuclei, because electrons are 1,000 times lighter than nuclei. So given the large difference in the mass between the atomic nuclei and the electrons in atom and molecules, we can separate their motion. And this approximation is important, is very important both for the calculation that we do in quantum mechanics, where usually we solve the Schrödinger equation for fixed nuclear position because the electrons are moving so much faster that we can consider the nuclei feeling an average field of due to the electron. And in molecular mechanics, that is the subject of this lecture, is use the Born-Oppenheimer approximation allows us to consider the nuclei moving on the averaged electrostatic field generated by the nuclei. In molecular mechanics, we approximate the atom to classical particles. The energy of the system is therefore calculated as a function of the coordinates of the nuclei. And we ignore, in molecular mechanics, the motion of the electron and the quantistic features of nuclear motion. With the most commonly employed method, the process that involve the forming and breaking of bonds and so involve electron rearrangement cannot be studied. However, I want to mention here that there are force fields, so-called reactive force field, of which I will not speak here, that allow somehow to simulate also the formation and breaking of some bonds. But let's say that these force field are not yet used in nucleic acid simulation. Let's see some generalities about the force field. When we use force field to simulate molecules, somehow we consider the molecules as formed by balls, that are the atoms, typically in coarse-grained simulation, but they can be groups of atoms that are connected through springs. And the energy of the molecule is expressed as a function of the spring resistance to deformation, so to the stretching of the bonds and to bending or contraction of the angles. For force field, what do we mean? We mean a combination of an equation, a functional form of an equation that express the energy function with respect to the coordinates. And importantly, the force field is not only defined by the form of the terms that we use in the expression, but also by the set of parameters that we use together with the functional form. In other words, we can have force field, different force field, very different force field, that have the same functional form, but different set of parameters. In the force field that are used to simulate biomolecule, especially large biomolecule, the most common terms that are used to represent the energy of the molecular system are due to, let's say, 4 contributions. One contribution, which actually comprises several more terms, is due to the non-bonded interaction, so van der Waals and electrostatic interaction. And then there are a set of bonded terms, which comprise the stretching of the bond, the bending of the angle, and the torsion of the angle. Each of these contributions is expressed by a mathematical function, which should possess 2 main features. Should be realistic, so reproduce the real variation of energy with the variation in the geometrical parameters, but it has also another important requirement. It should be computational, fast to calculate, because we can have a very accurate, very realistic function, but if they are not easy to implement in fast calculation, they can practically not be used for simulation for large molecule and for a long time. So let's see the term that we have in the force field one by one. For the energy associated to covalent bond, we know from the general chemistry course in both physics or chemistry undergraduate course that the potential energy, the variation of the potential energy with the interatomic separation represented in this graph in the ascissa can be adequately reproduced using the so-called Morse potential. The Morse potential has this mathematical expression where D of E is the energy value of the minimum, omega is the bond vibration frequency, mu is the reduced mass, and L0 is the reference value for the bond length. So here I go back to the concept I say previously. In a force field, it's important not only the functional form, but also the parameter. So in this expression, we have these four parameters. So the Morse potential is known to reproduce adequately the energy variation with the separation, interatomic separation of atom, interatomic separation. But the problem with this expression is that it's not computationally efficient. A simpler functional form that can be used to represent the variation of the energy with the variation of the interatomic distance when we are at a separation near the equilibrium value is the harmonic potential that is represented here. I guess all of you know it. And in this expression, we can see two parameters. The one represents the bond stretching constant and the other the bond length reference value. This approximation, as I said, is only valid for near equilibrium distance, because you see that as we move from the equilibrium, there is a large separation between the harmonic and the Morse potential. We can increase the region in which we reproduce the Morse potential through simple terms by adding other terms like cubic, quartic, and other and higher order terms. However, we have to pay attention because, for example, with the cubic function as a maximum which does not exist in reality. So if the bond stretch beyond this distance, there will be decreasing in the energy at increases distance, which does not correspond to the real behavior. Other terms can be added to correct this, higher order terms can be added to correct that behavior. Let's now consider the other bonded term, the angle bending. Similar to the bond term, the energy variation with a variation in the bond angles is usually described with an harmonic potential, so with an equation very similar to the one that we saw for the bond length. And similarly to what we saw for the bond stretching, we can include higher order terms to improve the accuracy. Let's stop shortly to do some consideration, to make some consideration about the difference in energy between bond stretching and bending energy. As we can see in this table, where is represented the value of the parameters for the harmonic potential, so the reference bond length and the force constant, the variation in of the bond length between two carbon with sp3 hybridization as a constant, strength constant, a force constant, which has a value of more than 300 kilocar mole per angstrom squared. While the variation of the angle, the bending angle between free carbon with sp3 hybridization is several order of magnitude smaller. So the energy variation with bond stretching are much larger than those connected with the angle bending. The third important term for the bonded interaction is the torsional term. In the organic or chemistry course, we learn that the energy of a simple molecule like ethane, represented in this figure, vary with the conformation, so with the variation of the dihedral angle between an hydrogen, a carbon, another carbon, and the hydrogen on the second carbon. The energy vary with the angle. And how does the energy vary? The energy variation with the HCCH torsional angle can be expressed with a cosine function, as shown in this picture to the left. For the simple molecule of ethane, where we have 2 carbons and 6 hydrogen. When we go to still a simple molecule, if compared to the biomolecule that is the subject of these schools, which is DNA, going from a simple molecule like ethane to another simple molecule like butane, the energy variation with the torsional angle carbon, 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 in butane there are 4 carbon atoms, can be expressed with a sum of cosine function. Now the shape is different, of course, being a sum. And we have different type of minima, global minima, so the minima with the lowest value, and local minima. Most of the force fields that are used for bioorganic molecules, and therefore for nucleic acids, comprise a term for the torsional potential that is formed by a cosine series expansion, as shown by this equation. To sum up, the bonded terms, here there is a little bit of Italian. The bonded terms are grouped in, are divided in three terms. One with an harmonic potential for the stretching, for the bending. Also, the stretching has an harmonic potential, as we saw. And for the torsion, we have a sum of cosine. The bonded terms are not, as we know, only one part of the interaction that are relevant for the structure, behavior of biomolecules and in general molecules. Atoms indeed interact not only through bonds, but also through space. And these interactions are divided, classified in two types, electrostatic and van der Waals. The electrostatic interaction are modeled typically, most commonly, using fixed partial charge on the nuclei of comprising the molecule. As we know, even in neutral molecule, the electronic distribution around the molecule is uneven. Here we have a representation on the molecular surface of this molecule, a representation with a color code to represent the electronic, let's say, density, the electrostatic potential. And we can see that there is a larger negative charge near these blue nuclei, which are nitrogen atom, here and here, and a lower potential with a green color on the other region of the molecule, on the hydrogen and on the carbon atom. In classic simulation, we do not have the electron. When we use in molecular mechanics using the force field, we don't have anymore the electron. We have particles which are typically centered at the center of the nucleus. And how do we reproduce the effect due to this uneven distribution of the electron? We partition the charges among the atom in such a way that the electrostatic potential that can be calculated with a quantum mechanical method is reproduced. The electrostatic interaction between two molecules or between different parts of the same molecules are calculated then as the sum of the interaction between pairs of point charge using the Coulomb law. So using this mathematical expression. Unfortunately, the derivation of the charge is not trivial. And there is no unambiguous way of determining the partial atomic charge. This is due to the fact that while we are used to think in terms of atom when we think about molecules, molecules are formed by different atoms. It seems an easy concept. In reality, there is no quantum mechanic definition of atoms in a molecule. There is not a quantum mechanic observable. So we can go back to understand this concept to this previous slide. Where does this hydrogen here end? What are the electrons that belong to this hydrogen? What are the electrons that belong to this carbon? There is no unique way to attribute a certain portion of the electronic distribution to an atom or to a nucleus or to another in the molecules. So, in other words, again, I repeat because it's an important concept, there is no an ambiguous way of determining the partial charges and several methods have been developed. One method is to calculate the electrostatic potential from the wave function through a quantum mechanical calculation, and then start from a trial function of the electrostatic potential originated putting the charge, a set of charge on hydrogen, another charge on oxygen, another charge on this other hydrogen, which should be equal to this charge, and calculate the electrostatic potential from the point charges, and then calculate the differences between the electrostatic potential obtained from the wave function and from the charge centered in the nuclei, and optimize the charge distribution, trying by minimizing this difference. But still, there are many ways to do this. So, let's go back again to the slide that I showed earlier. Here is represented the electrostatic potential with a color code on a certain surface of the molecule. So at a certain distance from the atom, but the electrostatic potential is in all the space surrounding the molecule. At which distance do I want to have the correct electrostatic potential? There are different schemes. So, for example, a scheme that is very used is the C-help scheme, and fit the charge in order to reproduce the electrostatic potential at several distances from the van der Waals surface that was represented in the previous figure. Another variant of the C-help method, the C-help-G, sample the electrostatic potential at points that are evenly distributed between 0 and 28 angstrom. The MK scheme optimizes the charges at different set of distance, and actually the result that you obtain using different system to obtain the charges can have a profound implication on the results that you obtain in the MD simulation. So here I show some molecule that we simulated 10 years and more ago, with the aim to use to calculate their free energy of solvation. And we tried a different scheme, and you can see that depending on the scheme, the result of the free energy of hydration, here are reported experimental, here are reported the computational, so a perfect agreement is on this line, vary very much with the particular method that is used. In most of the simulation that you find in literature using force field on DNA, you have a fixed point charge on the nuclei. So you have a charge typically at the center of the nucleus that is fixed there. However, we know that when, for example, we have here a molecule with a carboxylate group, here we have an oxygen, and which is has a partial negative charge. When a positive or negative particle is nearby, the electronic distribution on the atoms, near the atom, changes because there is a polarization that is due to the other charge present in the system. And in most of the simulation, in most of the simulation of DNA that you find in literature, this is not taken into account because the most used force field are based on fixed charge. However, there is an active area in force field development to reproduce the polarization also with a classical calculation, developing polarizable force field. Basically, we can divide the type of polarizable force field model in two groups. Those where is allowed a charge redistribution within each atom, and the second class is a class where the redistribution of the charge is calculated over the entire molecule together. The charge redistribution with each atom method are divided, there are at least two classes. In one class, we have an induced dipole or multi-point dipole or dipole on each atom. And in another very commonly used model, polarizable model, the Drude oscillator, we have an additional charge bound with a spring to the center of the nucleus that can move in response to the other charge in the system. The main limitation in using polarizable force field is the reduced simulation speed. Because clearly, in principle, using polarizable force field is a more accurate description of the distribution of charge in the molecules. However, polarizable force field are very costly. But there is an active area of development of polarizable force field based either on the classical Drude oscillator, and here is shown one important paper on concerning the development of this field, force field. And this force field can reproduce much better the interaction, for example, with small ions and nucleic acid. However, very costly. Another force field that can be used for nucleic acid and that is being developed actively is the amoeba polarizable atomic multipole force field for nucleic acid, which is on the other category of the polarizable model with the variation of the polarization on the atoms. With while at the moment they might be not really comparable in terms of computational power usage with fixed atom force field, it is a field, the parametrization of this force field is an active area and should be considered when simulating nucleic acid. It's also true that some limitation due to the polarization of a charged particle in various environments can be sometime reproduced without polarizable force field, but by simply scaling the charge of the charged particle in our system. So we are used to consider that, for example, let's keep it simple. A chlorine ion in water or common salt, kitchen salt, dissolved in water will have a positive cation with a charge +1 in the solution and positive and negatively charged chlorine with a unitary charge 1-. But in reality, when the ions are in an environment, not in vacuum, in a molecular environment, actually the charge that better represent their state might be less than 1. The other class of important interaction in non-bonded interaction are the van der Waals interaction, which are somehow in nature are electrostatic interaction, but not of permanent partial charge, on due to non-permanent partial charge of the atoms or atoms either isolated or in molecule. We know from the basic chemistry, that basic physics, that noble gases, which do not have a partial charge or electric multiple moments, have, in certain conditions, a behavior that cannot be described using the ideal gas model. And this is due to interaction between the atoms. Here are shown the interaction between two argon atoms. Here is represented interatomic separation, and here is represented the energy. At large distances, the interaction energy is 0. They do not interact. At small distances, we have repulsion. At intermediate distances, we have attraction. So we have long-range attractive forces and short-range repulsive forces. As clarified by van der Waals, the attraction at intermediate distance is due to dispersive forces that are due to the interaction between instantaneous dipoles. So let's consider the argon atom in vacuum. We can represent the average electronic distribution with as a spherical distribution around the nucleus. But even if an atom does not possess a permanent dipole, the electron can temporarily distribute in an uneven way, temporarily, because they are not fixed in a certain position. They can generate an instantaneous dipole, and an instantaneous dipole moment induce a charge polarization in the nearby atoms, and these generate the attraction. The quantum mechanics calculation suggests for the repulsive part of the energy function an exponential form. However, from the computational point of view, the most common way to represent these terms, attractive and repulsive and attractive, is through two terms that are represented in the figure, that are function of two parameters: the energy at the distance where the difference, the energy of the minimum of the curves, and sigma, the separation of the nuclei when the interaction energy is 0, going to negative value, attractive, to repulsive. you can find this expression expressed in a different way, but this basically the meaning, they can be interconverted one to another. But I'm saying this because you have to pay attention when you are looking for the van der Waals term of some atoms in your system. If you take the value from the literature, you have to pay attention that the value of the parameters are referred to this form or to this other. So if either sigma or Rm are given, with Rm being related to sigma by this expression. So you have to pay attention to, even if the functional form is the same, how the parameters are inserted in it is important when you actually are setting up the simulation. And another important things to which we have to pay attention when we want to use van der Waals parameter taken from the literature and using them in as input in our force field in the program that we choose is the type of combination or mixing rules that are used. Because for each atom type that we have in our molecule, and I will get into the definition of what it is an atom type, but let's say for each atom that we have in our molecule, there is one parameter epsilon and one parameter sigma, but which is the parameters for the interaction with another atoms of the same nature. How do we combine the Lennard-Jones parameter for different atom types? There are simple combination rules. So, for example, you can use either the arithmetic or the geometric average. And you have to pay attention if the force field that you are considering use for each of the terms, epsilon and sigma, the same type of average or two different type of average. Because using the parameters optimized for force field where are used this combination rule for epsilon and sigma, it will not be good for a force field that use geometric average for both terms. So it is interesting that only in 2006, even if the problem was already highlighted before, somehow it was observed how in simulation of DNA with simple salt used as counterion, I think here were potassium and chlorine. In the simulation, these authors that probably some of you know personally, observed that crystals of agglomerate of potassium chloride were formed. And this is not expected because it doesn't occur in reality. So why was it occurring in this simulation? This simulation, by the way, published in Journal of American Chemical Society. This was due to the fact that the parameters that were commonly used with the Amber force field using the Amber software were parameters that were adapted from a work where the parameters were optimize to have a geometric average for both epsilon and sigma, while in the amber parameters, in the force field used by these authors and many other, me included, in some work, these parameters were adapted to the Lorentz-Berthelot rules, and this adaptation didn't simply work out when potassium and chloride were used in the same solution. And due to this fact, a new set of parameters for monatomic ions has appeared in the following years, in 2008. These highlighted the importance when you are setting a MD simulation, the importance of carefully check the ions parameter that you are using, and also the importance of reporting in the papers that you write the detail of the force field that you are using. Unfortunately, some software somehow make it not so clear what parameters you are using. They can be used like black box. You ask for sodium, potassium, chlorine, the program add it, and it's difficult to find what parameters are actually used. But it's important to specify, because the result may vary notably with the set of parameters that you use. We have also simulated other conformation of DNA with quadruple helix, for example, and we have seen huge variation in the behavior and also in the effect on the structure, changing the ion parameters and the water model, because the ion parameters, each ion parameter is valid for a specific water model. So you have not only to check the ion parameters, but also for what water model they are optimized. Actually, the van der Waals parameters that are used in common force field like amber have been kept the same for the DNA for many, many years, even when the electrostatic term, the charges for the atoms in the nucleic acid have been changed, or other parameters like the torsional angle parameters have been changed. And recently, there is an active development of new van der Waals parameter with nucleic, for the atoms of in nucleic acid, like shown from this work that appeared in the literature at the end of last year online, where the van der Waals parameter for nucleic acid atom are updated, also taking into account the way the electrostatic terms, the electrostatic interaction are dealt with. So, as an example, pertinent example, Sergi in his excellent lecture mentioned the Ewald summation method, or the particle mesh Ewald method, Ewald method for calculating the interaction, electrostatic interaction. The force field, many force fields were developed before starting to use this method, and the van der Waals parameters were not updated since the regular use of the Ewald method became routine. And now there is a work to which I recommend to to all of us working in this nucleic acid community to pay attention in the development, in the evaluation of the use of this new set of parameters for the particular nucleic acid that we want to study using force field.
Francesca,
And
sorry to interrupt.
Yes.
You have 5 minutes. So.
Okay, thank you. And this development of the new accurate van der Waals parameter is, as I said, a very active area, and different protocols are used. Now I will skip some computational consideration, but I want to and also the Ewald, some details on the Ewald summation, because Sergio already mentioned it. Here there is summarize the form of a common force field used for biomolecules, like the Amber's force field. So we have here different terms, and while the functional form can be the same for Amber force field or charm force field or other force field, so the functional form, the set of parameters K1, E can be different. So a force field is defined both by the functional forms and by the parameters, and it is not a good practice to mix the parameters of one force field with the parameters obtained for other force field. When working with small molecules, there might be additional term, or even working with biomolecules for hydrogen bond or cross term that take into account the fact that if we vary the angle between a set of atoms, also the bond stretching might vary. And so there are force fields that take into account these. And collect the information that we have seen so far, considering that the force fields are often classified in three class. The class 1, that is the most commonly used for biomolecules, is the class with harmonic terms for bond angles. Class 2 is the one that contains anharmonic cubic and quartic terms for the potential energy of bond and angle and cross term. And class 3 is the class that contain terms for polarization or other effect, such as reactive force field. In the force field, we deal not with atoms, but with atom type. And this is simple to understand if you consider that, for example, these 3 molecules with 3 carbon atoms, we of course expect different stretching force constant for single, double, or triple bond, as we expect also different bond length reference, and this implies that we should use different atom type, different set of constant, different set of parameters for the each atom, depending on the environment where it is present. Here are represented, for example, the different type, some different atomic types for proton in the Amber force field, depending, they have different name because they have different parameters. And the same is true for the carbon types. How do we parameterize the force field? How we obtain the information to use as reference when optimizing the parameters? There are a set of, the most used technical data from small molecule X-ray crystallography, but also NMR spectroscopy. ER spectroscopy was at the starting of the force field development, but also thermodynamic data like density, heat of vaporization, and so on. And when we don't have experimental data, we can use quantum mechanical data as a reference. So I don't explain how the parameterization process works because I want to go to describe very shortly in the minutes that remain the force field for biomolecules that are mostly used. One is amber that I mentioned many times, and you can find it's also the software now is free to use. And unfortunately, you don't have a single amber's force field because here is schematized the evolution of the amber force field. Since its origin, the amber's force field in the 80s has been developed initially in the 80s, have been optimized in the 90s. 94, originating the Cornell force field PAR 94, that has then been optimized, adding specific parameters for the torsional angles in nucleic acid. Then these parameters have been optimized with when some bad behavior of DNA was observed, especially also making longer simulation, it was observed that several conformations were not as expected, and that this was due to the parameter used for the various torsional angle. And from here, we have the development of different force field, and the force field recommended now for the simulation of DNA are typically all 15, all 21, or BSC1, but recently has appeared a new completely parametrization of the bonded terms called 2MUC1 that has been completely reparametrized, taking into account the fact that both the charge obtainment and van der Waals parameter obtainment has been changed in the years. So before you choose a force field for your simulation, read the literature for the system you're studying, and if you can, check different force field against some reference experimental value, because there is really a wide variety. This is only for amber, but there are also other force fields like CHARM, OPLS that can be used. And the choice should always be done based on the problem that you're studying and the type of topology that you're studying. So thank you very much for your attention.
Thank you, Francesca, for very interesting and very clear lecture. Actually, there are so many force fields, and there are probably many questions. If we have in our conference hall, please. Okay, maybe in Zoom. And probably you are thinking about different questions. I would like to ask you, Francesca, about polarizable force fields in comparison with QMMM or quantum mechanical method. What is the computational cost if we compare QMMM or computational cost or a polarizable force field?
Please repeat the last phrase.
Sorry, probably the microphone is uncharged. the comparison between QMMM or quantum mechanical ab initio molecular dynamics and polarizable force fields. So we want to increase we wanted to increase to make closer our model to the real system, and we can do this using polarizable force fields, and also we can do this directly in our ab initio calculations. So if we compare these two different ways, how is different the computational cost?
Yeah, thank you very much, Sergio. Very important point indeed. Of course, using more and more accurate method lead us to use directly quantum mechanics, at least for part of the system, as in quantum mechanics, molecular mechanics calculation. Of course, if you want to, for example, simulate the equilibrium of an ion interacting with DNA or going to the solvent, you need the simulation time that are not allowed with quantum mechanical method on system of the size larger than a few base pair. So if you are working on a model system that is very small, you can use this method and check, but not necessarily you will have a better result. So it might happen that for your particular ion, you tried, for example, it happened to colleagues simulating lithium, for example, with the ab initio dynamics interaction with some phosphate. The results were not good at all, and the force field somehow can be better, but this is, you know, just seldom. The problem is that the computational cost when we want to use this method is too high. Especially if we want to simulate phenomena that occur in several nanosecond time scale, as are many phenomena that involve interaction of even small ions with DNA. So, for example, there are even sodium ion residence time in particular sequence of the double helix of DNA need several order of magnitude of simulation length larger than the 100 of nanosecond. You might need 10 microsecond, 100 microsecond, because the residence time are of the order of 100 of nanosecond. So if you want really to evaluate them well, you need very long simulation, and hence you cannot go to quantum mechanics. On the other hand, they also showed that for these ions, the polarizability is really important to model, to capture the real equilibrium, to capture better the equilibrium between interaction with the nucleic acid and dissolution in the bulk of the aqueous solution.
I see. Thank you. Thank you. And probably we have other questions. I do not see raised hands, but I have another one question. Probably you can comment about approach using machine learning for the development of the force fields, machine learned force fields. Is it used for DNA? Probably you found in literature such papers. As I know, this has just appeared maybe this recent years.
So I see that they are with soft matter. So machine learning are, I see they are developing very well for maybe a periodic system, or also in soft matter like metal organic framework. But to be honest, I didn't see anything with machine learning applied to nucleic acid force field.
I see. Okay, thank you. Me neither. So, but it's interesting. Okay, thank you very much. Let's thank our lecturer, Professor Francesca Mocci. And now we have a break for coffee, and we are not in our program, but it's okay. Let's start after 20 minutes at 12:40. So now we have a break. Thank you.
Thank you. Goodbye.
Bye. Okay.